Now let's turn to Sankhya. So Sankhya is one of the six systems of philosophy, and the literal meaning is numbers or counting. And in this, but if you study Sankhya, you'll also find a theory of matter, and the theory of perception and cognition and so on. So this idea of what numbers are and how we perceive the reality and what the reality is, these are intricately tied together. So if we take a literal counterpart or the closest counterpart of that philosophy in our modern understanding, there are two things that come very close. One is mathematics and the other is physics. So what I will try to do through this presentation is describe to you what the problem of numbers in mathematics is, and then try to describe some of the problems of physics. And I'll try to illustrate how these problems are very hard problems. They have persisted for centuries and they require a new way of thinking, but that way of thinking is inaccessible or unwanted in the Western paradigm of thinking, right? So let's start with the nature of numbers. I'll try to minimize this and see if I can. Okay. So counting actually involves 4 steps, and modern mathematics wants to describe numbers in 1 step. And I'll just come to that. So what are these 4 steps? These 4 steps are, I will call them identification, distinguishing, sequencing, and labeling. Right? So I will describe each of these steps in the next subsequent slides. And modern mathematics is only interested in discussing how to label things. And the prior steps of identification, distinguishing, and sequencing, these are the foundations on which labeling occurs. But these 3 foundations are discussed in Sankhya, but they are completely ignored in modern mathematics. So what do we mean by identification? And just as a caveat, I discussed with Ram how to pitch this presentation, and he told me that the audience is both broad and deep, right? So there are some experts, and there may be some people who are not necessarily experts, or they may be interested in things like that. So it's kind of little difficult to pitch something that is both broad and deep in a very short span of time. So what I've tried to do is keep it at a high level, keep it intuitive, as well as not lose the rigor or correctness and accuracy, right? So I will describe some of these things in a very simple way. Doesn't mean this is trivial, right? So if you have further questions, we can take that towards the end. So what is identification? It's the idea that there are individual objects, there are things in this world, and we don't have to know what those things are. Like in this case, I have depicted an apple, but we don't have to know that it's an apple. All just we need to know is there is a thing. This is how pretty much classical physics and even modern mathematics is concerned. If you go back to some of the history of the foundations of mathematics, they'll talk about objects, and they'll talk about classes. Classes then become sets, and an object is simply something. It doesn't have to be anything. So you can say A, B, C, D. These are objects, right? So this is an object. Now this is what we mean by identification. I have identified that there is an individual thing. I really don't know what it is. But this method sort of, stops working if we have to ask you to distinguish 2 things. For example, if you have an apple that's kept on a table, then you have to say that an apple is different from a table, even though in your perceptual field, you can only see a set of sensations, right? You can see some color, some shape, some size, and things like that. How do you know this color is actually an apple, and the table, for example, in this case, the apple is red. The table could also be completely red. This happens often in visual illusions where you cannot distinguish between the object and what's its background. You can say foreground and background. So we have to distinguish things, and that distinction requires us to invoke properties, just color, shape, size, taste, smell, and so on in physics, and all kinds of other properties are used like energy, momentum, so on. So distinguishing requires us to invoke a property, and we attach these properties to objects, right? And this thing, so object cognition, needs certain things, but at this time we just assume that it's an object. But distinguishing two things requires us to invoke a lot of properties. These properties then require concepts. For example, if you say I'm you going to distinguish an apple and an orange based on some concept, that concept can be color, it can be shape, it can be taste or smell and things like that. Then once you have distinguished two things, then you are required to sequence them. And what is sequencing? It's essentially prioritizing something ahead of something else. Like you can say, and the sequencing is not just for objects, it applies to many things. Like you can say my top priority right now is education, my next priority is my family, third priority is the nation, and so on. So by this whole process of prioritization, we come to what we can call a sequence. And each of these methods of prioritization requires a choice, right? So you can say that apple is first priority, orange is next priority, mango is third priority, or you can reverse that order. So these methods of prioritization are choice, and once you have prioritized them, then you sort of come to a sequence. So these are the three steps. You have identified, you have distinguished, and you have sequenced, and then the final step comes, which is called labeling. In that labeling, you say there's a first thing, there's a second thing, there's a third thing. And this is how you get first, second, third. Now, to be able to say first, second, third, you should have been able to say that there are two things, or in this case, there are three things. You should have separated out an apple and orange, and then you should have been able to distinguish them, identify them, distinguish them, prioritize them, and then you can label. Now this labeling, which you call first, second, third, in ordinary arithmetic, we also call the ordinal numbers, which is the first, second, third. And if you can say there is one, first, second, third, then you can say in the counting ends there, you can say there are totally three things, which is called a cardinal number. And cardinality or count is the result of using ordinal numbers. Now there are further steps. People say numbers. There are number systems like you can count to the basis of 10, or to the 2 basis of 16, and things like that. And we will not sort of go into that. We'll just talk about first, second, and third. Now, what is the fundamental difference between Sankhya and modern mathematics? And that basic difference is that Sankhya is focused on how to identify things, how to distinguish things, and how to sequence things. Sankhya is not interested in how do we label things. So there is no theory of what is 1, 2, 3, and 4. And that is why people sort of get confused and say, this is talking about numbers, but it is not talking actually about the numbers in which, in the way that modern mathematics talks about it, right? And therefore, sometimes people also talk about there have been Indian mathematicians and who have done great things, and before West did it, and so on. But they are not able to connect this sort of mathematics, which is about equations and algebra and computation, to this more traditional system, which is far older and traditional, which is Sankhya philosophy, because they are not able to connect this. So there is this big discrepancy that even when people talk about so-called Indian mathematics, they are not going back to the foundation of what numbers are and how did we come up with these. They are more superficially into the same system of number understanding that is currently followed in the West. So Sankhya talks about how do we identify things, distinguish things, and sequence things. And then once you have done these three things, then you get labels. And labeling is the result, but the foundation is something else. Now, there is a deeper anathema in Western mathematics, or the understanding of numbers, where they do not want to discuss or go into a foundation that is based on identifying, distinguishing, and sequencing. So what do they want to do? They want to simply construct a foundation of mathematics based on labels alone, right? So this is a simple illustration of how foundations in mathematics are constructed. I'm not saying this is the only foundation, but it's a foundation that's based on set theory. There's a very elaborate system, but I have to put it in a single slide so that everybody can understand. So I just put it in a simple slide. So this foundation says that we will begin with something called zero, and what do we do with, how do we define zero? We say it's an empty set, right? So there is a history of how numbers are based on set theory, so zero is nothing but an empty set. Then one is a set which has one member, which is the empty set, right? So if you look at the first line, then open brace, close brace, that's an empty set, and then you have an open brace, close brace with one member, which is the empty set or the null set, that is one. And then subsequently you can say that I will include 0 and 1 into a set, and that set has two members, which is 0 and 1, and we call that set as 2. Similarly, we can have a set that has 0, 1, and 2, and that set is called 3. Now, what is essentially going on here is that we have foregone that fundamental basis on which we intuitively, count things in an everyday sense. Because that counting is based on identifying things, distinguishing things, and prioritizing things. That way of counting has a human basis, it has a psychological basis, it has a mental and perceptual basis, but mathematics says we are not going to touch or understand or delve into any of that. We will simply try to do labels, right? So this is an attempt to create a foundation of mathematics using labels. What are labels here? There are two labels, open brace, close brace. By sequencing and combining all these labels, we are able to construct a variety of numbers. Now, what happens? We immediately get into a problem of circularity. And for example, if you say that I have a number called 0, the 0 needs two brackets, a left bracket and a right bracket. And this means that to define 0, I must have two brackets, and that requires me to define 2. Otherwise, if, for example, if you're writing a computer parser, a parser has to say that, it has to parse and look for a left brace, then it has to say that until if I get one more left brace, then, it's another set. If I get a right brace, So there is a choice always, is it a left brace or a right brace? That set of choices involves two things. But at this time, we are still with 0. We haven't defined 1, so how can we define 2? Right? So this is the problem of circularity in the sense that without defining 2, we cannot define 0. And yet, to define 0, we are assuming the existence of 2. Similarly, if you go back to the previous picture and you start looking at 1, this 1 is actually 4 braces. So to define 1, I need 4 braces. That means, I have not yet defined 2, I have not defined 3, but I am already assuming 4. Similarly, if you go to, as you go to higher and higher numbers, you are, leaping forward more in terms of numbers, and, you're never going to. So this is the problem of circularity. Now, mathematics disregards this problem, and it keeps proceeding into, the construction using labels. This eventually leads to the problem of Godel's incompleteness. This is a big topic, and unfortunately, I cannot go into that. But if you're interested, I have a book on this what is the problem of Godel's incompleteness and how it is related to sets and things like that. But essentially, even without understanding what is Godel's incompleteness, we can simply see a problem with the set theory, whereas I need to define 0, but I'm assuming 2. So why should we, study Sankhya? And, this question of why is very important. What Sankhya is, how can we understand it? These are secondary questions. The first question is, why should I do it? Right? What's the problem? And the problem is that foundation of mathematics is not in labeling. And we have mathematics is trying to create a foundation that's based on labels, but that foundation leads to Gödel's incompleteness. Right? So this is also well accepted, fact in modern mathematics. So if we want to create a foundation that is free of Gödel's incompleteness or free of paradoxes and contradictions in set theory and problems, and understanding the nature of numbers, we have to go back to thinking how do we actually count, and that goes to identifying, distinguishing, and sequencing. Now the issue is that to understand these three steps, we have to understand what is conscious perception, right? Because our senses and our mind and our psychology and whatever perceptual apparatus we have, that is used to distinguish, identify, and sequence. Right? So that is how we come to Sankhya. It is because there is a problem in mathematics. That problem is related to the construction using labels and so on. So this is the basis. Now, having dwelt a little bit on the problem of the nature of numbers and how that relates to Sankhya, let's turn slightly to physics. And like similar to mathematics reducing the 4 steps into 1 step, physics also does the 4 steps into 1 step reduction. And I will show you or try to describe how that reduction happens. So there are 4 tiers of reality. There are 4 tiers of reality which are called by different names in different places. Okay. In some places these realities are called Sthula Sharira, Linga Sharira, Sukshma Sharira, and Jivatma. Right? Sometimes they're called Vaikhari, Madhyama, Pasyanti, and Para. In yoga philosophy, this Vaikhari, Madhyama, Pasyanti, and Para, this terminology is used. And in Sankhya, Sthula Sharira, Linga Sharira, Sukshma Sharira, and Jivatma, this term is used. But we can connect these 2 things if we go back and understand what these things are. And I've described here a simple way to understand. This gross body, or what we call Sthula Sharira in Sankhya, is basically identifying stuff. And this body is, simply what you can call in physics objects. They are individual things. But the Ling Sharira, or the gendered body, is the senses, the mind, the intellect, and so on. They are the ones which are used to distinguish one thing from the other thing, which means you can ascribe them properties. So what we call the senses, they are different from the body, right? So your sense of smell, taste, and things like that. And why that is different is because that even when you are asleep, you can still see things. So your eyes are closed, but you are seeing. Similarly, you can feel fear or happiness and things like you can see emotions, you can even cry. So you are feeling everything independent, even when the body is at rest, your eyes are closed, your ears are, nothing is hearing, it's totally silent, you're able to see. And that is taken to mean that, the dreaming experience involves a sense, the mind, which is completely different from the body. But while the waking state, the body is used by the senses and the mind to perceive. Right? So it's a central problem of how you're able to see, feel, think, understand everything, even while dreaming, when none of the senses, none of the organs, so to speak, are active. So there's a difference between senses and organs. So these senses, they are required for distinguishing. Similarly, the mind. And so there's a very sophisticated system of how this whole perceptual process works. I'll try to discuss that, give you a gist slowly, here, but it's very difficult to. And then there's a process of sequencing. Sequencing simply means prioritizing. Like, for example, I gave the example, you can say my job is more important, and then my family is important, then my nation is important, then philosophy and all are last, right? Maybe not important. So there's a system of prioritizing. This system of prioritizing is also a subtle body, right? It is there in each one because everybody is doing some prioritization of their own. And and there are many ways in which you prioritize, like even ideas. For example, if you if you're if you follow reductionism of modern science, then it will say, well, at the fundamental level, there's only quarks and leptons. And from these quarks and leptons, we create atoms, then we create molecules. From molecules, we get biology, then we get life, and so on. So what is most fundamental? It's particle physics. And what is next fundamental is, atomic theory, or you can say theory of atoms. And what is next fundamental is chemistry, then biochemistry, then biology, and then, sociology, economics, and so on. So you construct that. So that is also a method of sequencing, in which you have said what is more fundamental. You have chosen that by a process of reduction. So there is we can discuss this system. This is probably months and months of discussion if you want to do that. But I'll just cap it here and move to the next one. So the key point here is that the three kinds of bodies and the transcendental soul. These are the four levels, and there are similarly four levels here, and sequencing, distinguishing, and identifying. Now, what mathematics essentially does is that, just like everything is in mathematics is reduced to sequencing, identifying, distinguishing, we reduce that to what is called matter in physics. But before we understand the matter, it's important to understand what these four levels are. So let's use some time to understand that. So what is Vaikari, or what is this thing that we call gross? Sthula is the word, but we can call it gross. So it's a space of individual things, but these things have no properties, or philosophy is called universals. And they're essentially in physics, like you can think of a space of particles, and these particles are all identical in classical physics, but actually they are not identical. In Indian philosophy, there is a very sophisticated system of how to distinguish these particles. But at the present time, this is just a space of classical particles, you could say. The other important thing is, in Sankhya, these particles are conserved, right? Now, before I speak a little bit about conservation, we have to understand what do we mean by reality in physics, right? It's that reality term in physics has a very precise numerical definition, is that if something is conserved, then it is real. So energy is conserved, therefore it is real. Momentum is conserved, therefore it is real. Charge is conserved, therefore it's real. Mass is conserved, so it is real. But particles are not conserved. Okay, so they are not real. Now people may not understand, because they say, hey, we have been studying particle physics, and but if something is not conserved, it is not real. It doesn't mean it doesn't exist, but it is not real in a very precise scientific and mathematical sense, that it is not conserved, right? Now this conservation or the non-conservation of particles actually leads to what is called indeterminism in classical physics. So if you normally in school and colleges, what they teach is that particles. So you start with two particles, they collide, and both particles move away, and that time you apply conservation of energy, conservation of momentum, and so on, and then you say you get a result, and that result is deterministic. But imagine you have two particles, they collide, and the total energy and momentum is distributed into three particles, or four particles, or 100 particles. So if the particles are not conserved, then mechanics is non-deterministic. And the simple reason is, more number of particles are created, therefore energy is divided into more particles, momentum is divided into more particles. The result is, if you cannot say that the particles are conserved, you cannot even predict how many particles, and therefore you cannot predict the result, right? So it's generally, it's taught in schools and colleges, and even sometimes in universities, that classical physics is deterministic, and that is not true, because there is no fundamental principle in classical physics that says particles are conserved. Only there is energy, momentum, angular momentum conservation. So this is what we mean by Vaikari. Vaikari is something, there are particles and they are conserved, which is different from classical physics, where there are particles and they're not conserved. Now what is Madhyama? Madhyama is our vision of saying that there are particles and they have properties, right? So modern science uses properties like charge, mass, momentum, energy, and so on. And Sankhya uses different properties called smell, taste, sight, touch, and each of these have many, many divisions. So there is a system of hierarchy of how properties themselves are constructed. The similarity between these two things is that both science and Sankhya, they will say that these properties are conserved. So both of them are saying they're real, right? The difference is simply that physics will say, momentum is real, energy is real, angular momentum is real, and Sankhya will say none of that is real. The real thing is taste, touch, smell, sound, sight. Now, if you go into Western philosophy, which existed before Newton's formulation, and primary discussions about what is empiricism and how knowledge can be acquired by observation. These discussions that happen. There are ample number of objections to this idea of what is called primary properties, right? So this distinction is created by David John Locke. He says talks about primary properties and secondary properties, and he says that taste, touch, sound, smell, sight, smell, and so on, they are secondary properties, and length, mass, momentum, energy, all these things are primary properties. Now, the nomenclature is done such a way that primary sort of has, it sort of indicates in a way that this is reality, and secondary is something that's created. A philosopher said that, hey, you never actually perceive, energy, you never perceive momentum. All you see is something called speed. And the way you know speed is that you see something moving, and then the way you know something moving is through sight or through touch. But you never actually know any of these properties. So how can you call these things real? And there is, at least a 500-year debate which is unsettled even today on how can you claim that any of these properties like, mass, charge, energy, momentum, they are real. If anybody is interested, then I can go deeper into that. But otherwise, I'll just move on and say that there are two classes of properties, primary and secondary, according to the Western nomenclature. Sankhya says the secondary is real and the primary is unreal. And science says that the primary is real and the secondary is unreal. Right? So if somebody has looked at the Sankhya and Science book, this is the thing that we start discussing from. Now, what is, so one more thing. So we got particles with, we got particles with properties, but there is no sequence between them. There is no order between them. It's just a space. You don't know where the, which one is first, which one is second, and so on. That thing comes in when you inject a coordinate system into the space, right? So you say that origin is the first. And then I will, let's say, count things along the x-axis first, then along the y-axis next, along the z-axis. So then you start. So basically, to say that there are a system of particles which have some properties, then how do you sequence them? This arises when you inject a coordinate system. And so now you get all the three things. You got individuals, you got their properties, and you got a sequence between them. Now you can count. Right? So, because physics assumes that there are particles, there is a space, and there is a, not just space, there is a coordinate system using which we can count. Therefore, what you see, what you are told, or what we are taught in schools and colleges is this very simple system where you say there is a space, coordinate system, and particles with properties, and that seems like just one thing. But there are layers of three levels that have gone into this construction, which are sort of not distinguished, discriminated. This is there is another distinction between Sankhya and physics, which is that we say that these coordinate systems are conserved. So they are real for Sankhya, but they are unreal for physics. Okay, and what I mean by that is, like, for example, I talked about we having a prioritization system. There is a lot of divisions, subdivisions into what kinds of sort of prioritization systems we have. So we have one prioritization system for ideas, another system for actions. Which action should be done now, which should be done later, right? Similarly, we have a prioritization system for our desires. What desire should I fulfill today, what tomorrow, what later, what is my long-term goal, what is my short-term goal, etc. So there are many ways in which we are ordering things. Similarly, which think is more important, which is less important, what is near, what is far. So there are many systems of prioritizing, and all these systems are conserved. So we say it's real because it is conserved. And this conservation, it becomes a big problem of liberation and things like that, because whatever choices you have made in the past, they interfere with the choices in the future. And so we'll briefly discuss that if somebody is interested. But that's the connection between this thing and the spiritual understanding. So anyway, now what is we call the para? So we talked about Vaikhari, Madhyama, Pasyanti, and para. Now this para is basically choosing a prioritization system, right? So I can say that I have a priority in which my career is more important, my family is next important, my nation is next important. That's a prioritization system. But I can change my priorities. That priority is, the idea is that all these prioritization systems are already existing. It's like a space of coordinate systems. And what we call the Pasyanti is a space of coordinate systems. And in that space, there is a choice by which a coordinate system is selected. And thereby a system of priorities is selected. And by that prioritization, selection of system of priorities, we create an order in which you say this is more important, less important, this is near, that is far. And from that, you perceive properties. Even property perception is, you can say that I focus more on color and I look at shape next. Somebody can say I look at shape first and I look at color next. Similarly, I can say that I will distinguish things. I'll go to a shop and I'll look at the quality of things, and if I like it, price doesn't matter. Somebody else can say, I will look at the price first and then I will look at the quality. Right? So this perception or this counting, this ordering and sequencing and numbering problem is an extremely complicated problem. But because it's simplified or reduced to labels, we don't understand. So so what science does is essentially it says that this coordinate system is nothing other than a particle, right? So, and because the particles are not conserved, therefore the coordinate system is also not conserved. And therefore, whatever we call the soul or things like it becomes a particle. Particle is not conserved, therefore soul is not real. So in one picture, we can draw simple comparison of, just like we did for mathematics and Sankhya. We said that there are 4 levels of, by which you arrive at a counting or a number. And in physics, this is what happens. There are 4 levels still. The particles, their properties, their priorities, which you can call a coordinate system. And there's a choice of a coordinate system. In Sankhya, we'll say all these 4 things are conserved. So particles are conserved, properties are conserved, priorities are conserved, and choices are conserved. In physics, you say only the property is conserved. The particles are not conserved, which just leads to indeterminism in all of physics. Then you say even the coordinate systems are not conserved. And of course, there is no observer because the observer is nothing but a particle, and that particle is not conserved. So just like in mathematics, these sequencing, distinguishing, identifying are just reduced to a label. In this case, even the 4th thing, which is the soul or the observer, is reduced to a label. So if you say, who are you? Nobody generally says I am an Atma. They will say my name is so and so. So who are you? Oh, I am Ashish Dalela. What is Ashish Dalela? It's a label. It's a label, which is a name. You can also say number. It's like you get Aadhaar card and you get a number. So who are you? What is your personality? It doesn't matter. What are your choices? It doesn't matter. What is how you perceive things, your individuality? All that doesn't matter. You are reduced to a number. So this is, and that's how society runs today, and because you don't ask what those things are, just reduce everything to a number. So you get a number and then you get all the details subsequently. So this is also happening in physics, right? So you say, what is this object? And you would essentially say it has some number which is mass, it has some number which is charge. So it's a collection of numbers, and this collection of numbers can essentially be, in a suitable ordering system, it can also be reduced to one number. And so all that you get is, what is reality? It's a collection of numbers, right? In that system, a particle is equal to a property, is equal to coordinate system, is equal to choice, and finally everything is a number. Right? Now, some people might say, no, physics has, conception of properties, like we'll say there is mass, energy, momentum. The answer is no. These concepts that we use in physics, like, let's say you say mass. What is mass? Okay, nobody can explain actually what mass is. All that we say is that if you want to measure mass, go to Paris. There is a standard kilogram kept in a museum. That kilogram is what we mean by mass. If you measure against that kilogram, that is the definition of mass. And this is a big philosophy. It's called operationalism. There is a Nobel laureate, who was the pioneer of this philosophy. And what they essentially said is that he was trying to measure pressures. His name is Peter Bergman, and he was trying to measure pressures. And he said, I get a gauge, to measure pressures, but it fails after a certain number. When the pressure increases, then the gauge stops working. Therefore, I don't know if the gauge is wrong or the pressure is, or the value that it's indicating is correct. Therefore, there is no meaning to pressure other than the gauge. So if I have to pick the right gauge, that gauge itself means pressure. That defines what we call pressure. So this is not something trivial that, we are taught in school and colleges that science, there's a property called mass and charge and things like that. Answer is no. There is no such property. It's just language that we use to create some, philosophical system. But ultimately, if you go down to the brass tacks, say every property is nothing but an object. That object is not also a general concept. It is a specific thing that is kept in some museum. Okay. So everything comes down to a label or a number. Now, what Sankhya does essentially, it describes a system of hierarchies, right? And we saw 4 levels in hierarchy, where you start with particles, then you get properties, then you get an ordering system, then you get a choice of an ordering system. So this is not the end. There are many levels inside this hierarchy, right? So again, Pasyanti Para, Vaikari Madhyama, Pasyanti Para. There's a complicated system. There are 16 ways of identifying what we mean by particle. This is what is called, and there are 24 ways of distinguishing based on different kinds of properties. There are eight methods to sequence. Like I talked about, there is a method to distinguish your desires, your knowledge, your activities, and so on. So there are 8 different methods. Similarly, there are 2 methods of that method is accept and reject, which you can call a choice. There are 2 methods by which you can pick a sequencing system. So each of these methods are comprised of many individual levels. For those who kind of know or nuanced into this whole system, if you add these up, the 16 plus 24 plus 8 plus 2 is a 50. This is very closely tied to our system of language, in which we said there are 50 alphabets. All these alphabets are indicating some property, some method of distinguishing, some way of identifying something, or some way of choosing. And these 50 alphabets constitute what we call the Sanskrit alphabet. I'll not delve into that, but just as a side question. Now, this is not, again, enough. Each of these levels is divided by further 3 modes. Like I can give you an example of what is a car. So a car can be described in 3 ways. And this problem, if you're interested, it again comes up in mathematics. So you can say, what is a number? So you can say, what is 2? And sometimes you say two is a general concept. Sometimes you say two is a specific individual. And sometimes you can even, in computer programming, you can even treat two as an instruction, right? So uh, if you have fundamental instructions, so they are also labeled by numbers. So when you get a program, you get ones and zeros. They are numbers, but they are not quantities and they are not concepts. They are instructions, right? So similarly, this problem actually leads to many paradoxes in computer science and as well as in mathematics. So this is what the book Godel's mistake discusses, because we can use number as a concept, as a quantity, and as an instruction. And these three ways are essentially due to the three modes of nature. And these three modes can be intuitively explained. You can say, what is a car? You can say car is nothing but a set of properties, some shape, some size, some weight, some color. This is what we call knowing the car. And somebody can say, no, but what if the car just something looks like a car, but it never works? Can you really call that a car? So he said, no, car must also run on the road to transport some people. So that is also a definition of car. And then you can say, well, you have just defined, concept as some set of properties. Maybe it's a design, maybe it can be designed, but there are no actual cars. So then there's a third mode, is called the thing mode. So there are three modes. There is an idea mode, there's an activity mode, and there's a thing mode. The same thing exists in numbers also. You can treat number as a thing. You can treat it, as an activity, and you can treat it as an idea. Now, when Godel constructed his incompleteness proof, he used the thing mode and the idea mode, right? So he took sentences and he labeled them to digits. So he said, this is a sentence, it has a meaning, and then let's label that to a number, which is called the Godel's numbering thing, or Godel's numbering scheme. And that, using that scheme, he created a contradiction between an idea and a thing, right? And that contradiction is essentially like saying, let's say you have, somebody named Mr. Barber. Okay, his name is Mr. Barber, but he is not a barber, right? He may be a carpenter or he may be something else. Then there is somebody called Mr. Carpenter who is actually a barber, right? So you can have a name that is not the nature of the thing, and you can have a nature of the thing which is incompatible with the name. So that requires you to say that there is a mode in which I will think about the thing, and there is a mode in which I'll try to understand the property. The name and the meaning are two different modes, but you can't do that with numbers, right? So this is the source of many paradoxes in mathematics. In any way, so there are four levels in which that there are sub levels, and in each sub level there are many modes. So it's a very sophisticated, and every problem of philosophy or mathematics or physics is addressed. Everything is, it's a necessary, thing. It's not something superficial, or we just added it for the heck of it. Now, instead of going and delving into this hierarchy and description and all these details, it's a very long and complex process. I will simply try to summarize what this hierarchy essentially achieves and try to see what it means for physics. So what does hierarchy achieve? Essentially, it transforms independence into dependence. And what we mean by that is that if you study classical physics, you will be taught about something called independent particle. All the particles are independent. So the first thing we teach in Newton's first law is that there is an independent particle. So there is only one particle in the whole universe, right? You can visualize like that. And that we call that as a free particle. And we say that, particle undisturbed by any forces continues on its trajectory of motion. That's the first law of Newton's first law. What is Newton's first law essentially saying? It is saying that the world is comprised of independent particles. And then there is force on it and things like that. But the reality essentially is all independent particles. That is what that's what continues into classical physics, all over classical physics, until you get into quantum physics, where this fundamental idea that there are independent particles itself is challenged. And because things are no longer independent, they are no longer even interacting through forces, right? So the second premise that there are independent particles interactive forces. So this problem of non-independence, which was postulated, or independence was postulated in classical physics, begins to break down, and we are not able to understand why it breaks down, because we have assumed that things are independent, right? Now hierarchy, what it does is it transforms that sort of independent concept into something called dependence. Now this dependence is relative. If you have steep hierarchy, then you have a lot of dependence. If you have if you have no hierarchy, then this is complete independence. So this hierarchical description of matter creates structures in addition to what we can call particles or things. These structures themselves have interactions, which is completely different laws of science about how structures interact with each other. Right? You can think of two companies, two organizations, two governments. They have structural, and there are a lot of people who study systemic behaviors, which is to say that doesn't matter who the person is in the government or who the person is in the organization, the structure of the organization is such that the person is helpless, right? So this is the structural way of thinking. Then I'll make the final point is that all of classical physics and even quantum physics is based on this fundamental idea of uniformity of space and time, uniform homogeneity and isotropicity of space and time. So what does it mean? You're taught this law of conservation of momentum, right? What is this law actually? Is there really a law? The answer is this law of conservation of momentum is nothing but saying that the space is homogeneous, which means that the distance between point 1 and point 2 is equal to the distance between 2 and 3, 3 and 4, and things like that. So what happens if you compress this? What happens if we elongate it? The answer is we can never know, because we are inside that space. So conservation of momentum is nothing but the hypothesis that space is uniform. Similarly, conservation of angular momentum is nothing but the hypothesis that all the directions in space are or the directions in space are the same. Similarly, conservation of energy is nothing but the hypothesis that all moments in time are nothing but they're essentially identical. So there is, like, you go 100 years from now, you can say history has time has passed and things like that, but essentially time is what we call time in the physics sense, is all the same. So I've talked about this, but if you delve into this, you can say that physics is simpler. There's particle and four properties, essentially all these properties reduced to what we call space. The answer is Sankhya also is just the understanding of the nature of space. But that space is immensely complicated because it tries to explain all our experience. As a simple example, we construct a coordinate system to say what is first, second, third, fourth, but that is only for particles. What if we say that, hey, you have desires and can you prioritize your desires? You have ideas, can you say which is a more fundamental idea? You have activities, can you say which should you do now, which should you do later, which should you not do, right? So if you take that full conscious experience and then try to fit it into the paradigm of coordinate systems, obviously that system will not work, right? And so this is necessary complexity. And so now let's, there I have, I think, three or four more slides. I'll try to apply these ideas of hierarchy to scientific problems, okay? So let's illustrate, there's a second law of thermodynamics, which says that entropy always increases, right? Now, what is entropy increase essentially? It is saying that the total energy is conserved, which is the first law of thermodynamics. The second law says the entropy increases. So total property, which is properties in energy, is an example here. That is conserved, but the particles are not conserved. And if you go into statistical thermodynamics, you can study this, that this any system is drawn into a phase space. The phase space can expand or contract. That contraction or expansion of the phase space is essentially the number of particles are increasing, right? So physically, you can say that energy is the same, but phase space is expanding. That expansion is called entropy increase. That's number of particles are increasing. So what is this entropy change? Is essentially number of independent particles have increased. And how can they increase? Because classical physics this is okay with classical physics, because classical physics or Newton's physics never said that particles are conserved, right? That claim was never made. So in thermodynamics, that claim is upheld and said, well, it is not conserved, but we are saying it can increase. And that's therefore classical physics and thermodynamics they make slightly different statements, but they're totally compatible. But the issue is nobody knows why the number of particles should increase, right? So there is some reversible processes where the particles don't increase. There is some irreversible processes. So we just say that it's a law of nature. It can the law of nature is not said that entropy will increase. The law of nature is that entropy cannot decrease, right? So second law is more appropriately stated by saying the entropy shall never decrease. So if you want to think of, Sankhya, and try to apply this to thermodynamics, we will think about this problem in a completely different way. And we will say that particles are not increasing, they're not decreasing, right? Because these particles are conserved. What is changing is that the particles are becoming more independent or dependent. So if they become more dependent, the hierarchical structure is created and you call that order. Similarly, if they become less dependent or more independent, hierarchies decrease, you call that chaos or disorder. And that's what you map to entropy increase and decrease. So essentially, what is happening is in some systems or in physical processes like engines and things like that, entropy is said to increase, and that's essentially our way of thinking would be that its independence is increasing, which means the structure or what you call the order is breaking down. And these terms like order and disorder have the structural connotation, but nobody uses that in a real physics sense. They just use it in the sense that number of possible states which are defined in the phase space, the phase space is expanding, therefore entropy is. But if you think in terms of this structural, way of notion, then you can say that nature is not necessarily headed toward disorder, which means that entropy need not always increase. It can also decrease. And that decreasing is to say that if the hierarchical structure increases, then the entropy can decrease. So just by changing the way you describe order and disorder as hierarchy or non-hierarchy, you can say that entropy need not always increase. It can also decrease, and that system of increase can exist in other systems such as biological systems. And that has huge implications for how we understand life and biological systems. Then the next thing is quantum probability problem. This is again a big, I have done an interpretation of quantum theory if somebody's interested. It's a multifaceted problem, but let's just talk about what a simple problem which is called non-locality. And this non-locality is essentially non-independence, right? So this creates a big problem because we are used to thinking in terms of classical physics where everything is independent, right? You have two electrons, one has a positive spin plus half spin, the other one has a minus half spin, and we think that these are independent things. But we don't, in Sankhya, we would say it's a hierarchical structure. It's part of a system. That system is, what we mean by the system is there is a third thing which actually creates this structure. And that third thing, so if you change the state of one particle, the state of another particle is also changed. Now that thing, that the third thing is not a hidden variable. Is I want to make that point because if some people are there, they might immediately think of it as it's a hidden variable. It's not a hidden variable. It's the way you create structures, and that requires some deeper delving into the nature of Sankhya, that these particles are actually symbols of meaning. And I can give you a simple example. You can think of a book, right? So you are doing a quantum measurement, and right now we think of it as a physical system of particles, but you can also think in terms of a book. So a book has, if you don't understand the book, what the book's meaning is, you can say that there's a 2% probability that the word "the" will occur in this book. there's a 0.5% probability that the word probability will occur in this book. So in this way, you can reduce a book to a recurrence of probabilities of the words or alphabets, whichever way you prefer. So, but the book is not simply a system of probabilities. It is actually a structure which has a hierarchy. It has hierarchical structure, which is basically chapters divided into sections and subsections and paragraphs and sentences. So there's a hierarchical structure. But if we flatten the structure, we say there is no hierarchy, then all that we can do with this, I can only predict that the word X, or the word ensemble will occur with some probability, the word existence will occur with some probability, and all that I get is certain probabilities. But if you want to solve the probability problem, we have to say there is a structure. In that structure, the things that are in the dominant position. For example, the book is about physics. You can say particle and wave. These two words will occur more frequently in a book on physics. But if you were talking about the book on economics, then the word money and free market will occur frequently, right? So that depends on. So again, quantum probability problem is essentially, in our way of thinking, is about we looking at matter as something without meaning. We treat matter as a stuff or box or object or whatever. But we look at, Sankhya will look at the same world and saying we are reading the world like the book is being read, right? So we study the nature like a book, whereas physics studies the nature as, instead of reading the book, it says what is the weight of the book, what is the mass, what is the length of the book, what is the height of the book. So there's a difference between studying the book as length, weight, mass, and reading the book, right? And if you are going to simply measure length, weight, mass, and things like that, you cannot understand what the book is. Therefore, that system is horribly incomplete. You have to start reading the book, then you can understand why the words occur in a particular sequence. So I just, this has been long. I think I maybe overstepped my time, but this is just a glimpse. I have several books, and I can, if you're interested, there are numerous applications of a new way of thinking about this to ordinary subjects like cosmology, chemistry, social sciences, number theory. I've applied these ideas to several fields, and in each field, there are two things that you can do. One is you can demystify the problems that nobody else is able to demystify, right? And then you can even say that how you can solve this problem, right? So both things you can do. That is, as Ram was saying in the beginning, that is the way to do science without saying, we did science in the past, okay, and we don't know what to do now, or saying that we were better in the past and you stole from us, or saying that I don't care about you. All these things are not required. We can do better science today in the areas where you are failing, or somebody, materialism is failing. So we can do better. This is it's a scientific approach, but it is still outside the current materialism, paradigm, which is sort of irrational and empirical, because it's a dogmatic system where you say that I will not look at anything other than, the way I have been looking at things in the past, right? So that needs a change, and India can, Indian universities, Indian education system, you can say that we have thought about these things in the past. We have a different approach to these things, right? This approach we can drive, and we can demystify the problems. I'm not bringing in, soul or God or spirit or, mind unnecessarily. It is necessary complexity. I'm bringing that, and it is useful complexity, right? Because I'm able to demystify your problems, I'm able to solve the problems, and I'm able to show how they can be solved, right? So this is, I'll halt here, and I'll take questions. I hope this was useful. By the way, I have a website. It's called Shabda.co. You can go there. There are several things there. There are lot of blogs you can read about if you're interested. There is a place you can ask questions if you're interested. There's the forums. So it's forums.shabda.co. You can have discussions. Many people come there and ask a lot of things. And there are other things also, but and there's a books. So everything is on Shabda.co. It's very easy to remember. So I'll stop here, and Ram, over to you.